Hello everybody! I hope everybody is having a wonderful day. So, before we get started, just want to remind you that this is the last week of material that I'm going to be covering for the course. So, this week I'm going to be talking about counting. So, today we're going to be talking about basic counting principles, in particular how you can count elements of a set, and then we're going to talk about very specific ways, like what I would consider somewhat special cases, or more specialized types of ways of arranging or counting objects when we start talking about things called permutations and another set of things called combinations. So let's get started here. So I want to start off with one of the more fundamental rules of counting. It's called the multiplication rule. So imagine I give you some positive integer k, and imagine I give you a sequence of choices. I'm going to call the first one a first something, the second one a second something, the third one a third something, and I'm going to have up to maybe k of these. So I'm going to have k choices to make. And these choices are going to ultimately determine which ones I get to pick from. So the multiplication rule says the following. So if there's n sub 1 ways to do the first something, n sub 2 ways to do the second something, n sub 3 ways to do the third something, and n sub k ways, so all the way up to n sub, up to our kth one, n sub k is the number of ways of doing the kth something. So the total number of ways to do all of them, say the first one, the second something, the third something, the fourth something, the fifth something, all the way up to the kth something, is going to be the product of each one of these n terms. So it is the product, so it's n sub 1 multiplied by n sub 2 multiplied by n sub 3 multiplied by n sub 4 multiplied by n sub 5 multiplied by n sub 6, all the way up to n sub k. So I've denoted that here with the product notation here. So this looks like a bit of a mouthful because I'm saying some things. Like, what does that mean? So I like to think about this as a task that I've given you that consists of a sequence of choices. And each one of these has a number of ways that you can do the something. So that's one part of it. The other part of it is that you got to think about this also like a set of operations, a multi-step operation. So imagine you have yourself the possible ways of choosing a something. So there's a way of doing the first something. Now, it's going to be very important that each one of these somethings doesn't change depending on a previous choice. It has to remain constant. I'm going to talk more about what I mean by this later, but I'm just going to reiterate what's literally on the slide here for you because I think that it's well put enough there on the slide. That the possible ways of perform a step may depend on previous steps. So keep in mind, the steps could depend on other ones. However, the number of ways, so that's the most important part, the number of ways to perform each step must be constant. This means it doesn't fluctuate, it's just constant. The number of ways it can be done is constant for that particular step. And this is regardless of the previous actions. So let's start talking about something simple here. So, imagine here. I'm trying to pick up my clothes for the day. Now, naturally, I need to figure out a sequence of choices. Now, I don't necessarily have to do them in this order, but I just really want to, I need to pick up my clothes. So, usually I have white socks and black socks. So I'm going to denote this as white. W and B. Then I'm going to pick up some underwear. And now keep in mind, I've been doing a lot of traveling. Let's just say I have just one. I assure you I do not, but I think it's fun. just don't go with one. I assure you. Hence my emotion there right after it. That's what I'm denoting it by. That would be your expression, I would at least hope. So then I have to pick up some pants. So I have a blue pair of pants, I have a beige pair of pants, and I have a gray pair of pants. Then I ultimately need to select a shirt. Now, like I said, I didn't imagine this scenario. I didn't pack up really that many shirts. Some reason I only brought teal ones and pink ones. I don't know why, but I guess I just did. Woo! Either way, that's quite a trip. So anyways, if I were to go out and pick each one, notice that each one of these is a sequence of choices. So in the first one of my options here, so think of this as the first operation, I need to select either a white pair of socks or a black pair of socks. So that's the first step. Now, you're going to notice at the bottom here, so you'll see it right about here, you'll see that I've laid out what looks like what some would call a decision tree. So I'm just mapping out the decisions that I'm making at those times. So you notice that I start off at the start point. So I'm at the start. And then what I want to do is I need to make my first choice. So either I go white or black. So I have two choices to make in my first operation. Next, so I notice it branches off like that with two branches leading from start there. Next, I got to pick out my underwear. Now, unfortunately, I only have one, so there's not really any choice to be made. I'm just going to wear it, right? So that's the second step in my my sequence of operations here. So you'll notice that for each one of these, I only had to make one choice, given that I picked a white pair of socks and given that I wear a black pair of socks. So notice that there's no branching out at this point. It's just I have my two possibilities. I could have at this stage picked the white pair of socks or the black pair of socks, but each one of these I have to pick the underwear, right? There's no choice in the underwear, unfortunately. We're not that lucky. So next I need to pick some pants. Now there's a possibility that I can pick a blue pair, a beige pair, or a gray pair. Now, that means I have three possible choices for my third step. So that means that I either pick the blue one, the beige one, or the gray one. Now, remember, I've already picked a white one or a black one, and I've had to accept just one pair of underwear, right? So you'll notice that in my diagram here, you notice that I fork out three possibilities where I pick either blue, beige, or gray. See? And then lastly, the final step is I have to pick the shirt. So it's either teal or pink. So you'll notice that they'll branch out like this. But I want you to observe something. On the furthest most right side, notice I draw a whole bunch of them, and they all line up at the same spot because they all require a decision. Ultimately, that's based on previous decisions. Now, not necessarily that they have to all line up like this, but it makes it much easier to count them using this rule. So notice that each one of these, if I were to count up each one of those dots over there, on the furthermost right side after the fourth step, you'll notice that I have 1, 2, 3, 4, 5, 6 on one side. So notice the other side is symmetric with this. So actually, I noticed that one of my arrows, for some strange reason, is pointing to P down in the bottom two ways. I actually should be pointing up to the T there. But either way, there's 12 possibilities. And I've just displayed all possibilities to you in that tree there, or process tree. So, how exactly do we use the multiplication rule here? Well, notice in the first step, I have two choices to make, the white or the black socks. So that's n sub 1. N sub 2 is just 1 because I just have to only pick one pair. I only have one underwear. That's it. I'm out of luck. You don't want me to make other alternatives. Promise me. And then step 3, I have 3 choices to make, right? So n sub 3 is going to be 3. And for the fourth step, I have 2 choices, right? I have 2 possible shirts I can pick from. So that's n sub 4. N sub 4 is 2. So notice that I get, if I apply the multiplication rule, I get 2 times 1 times 3 times 2, which is equal to 12, which happens to line up with the number of the possible states at the very end of the process. If I look and follow down each one of those paths, I get one possibility. But if I notice I count up all the ones at the very end, I get all the possibilities. So in this case, I get 12 possibilities. So this is just a simpler example of how you can do some multiplication rule. I've just drawn it out here so it's easier to see it. So notice that, now one thing I want you to notice is that at every one of these steps, you'll notice that the number of choices that I make, it doesn't change between the possible choices that I make at a given step. So notice that in step 1, when I have the white shirt or the black shirt, I never actually change the number of possible choices, right? There's only one choice for either one. Likewise, when I pick the underwear for step 2, I have 3 choices in my third step to select blue, beige, and gray. Notice that number, now it could be different numbers. Sorry, it could be, my apologies. It can be different objects, but they have to be the same number of choices. So notice that in either case, I still have 3. And step 3 to step 4, I only have 2 choices, right? The teal or the pink. There's no change in this. I want you to keep that in mind for my next example. So here's another example here. So imagine you're working at a grocery store and you have cashiers, and the cashiers have the 3 following rules. They could be a general cashier, so this is just somebody that works at the till, and they don't necessarily have to worry about other types of tasks. They just work at the till, just helping with groceries. The second is the cash office role. They often play a very important role. And the third one is the float. So these are sometimes people that will work on the till, but sometimes they also have to go around cleaning or maybe going for walks around just to make sure things are operating just fine, usually just doing smaller tasks. So we have 3 different roles here. Now, imagine I have 4 workers. Now, I just want to determine what these 3 tasks should be assigned to for the 4 workers. So keep in mind, let's just pretend that the 4th person has a role somewhere. We'll just assume that whatever they don't get it, they get the cashier role. So I have 4 workers. Bob, which I'm going to denote as B. Alice is going to be denoted with A. C is going to be denoting Charlie. And Drake is going to be denoted by D. And I want to have the following constraints in place. Now, imagine me. Imagine I'm the employer. Ooh. Imagine I'm the employer. And I tell you that Bob is not qualified to work as a float worker. See, Bob is really good at just working at the cash till, but really not very good with people beyond just working at the till. I don't know. This is just between you and me. You would not tell Bob this. It would just hurt Bob's feelings. So that's the first constraint. The second one is that either Charlie and Drake, so one or the other, must be a cash office. Because maybe the employer, maybe I trust Charlie and Drake a lot with the money here. So how many ways can I assign the work roles given these 4 workers and these constraints? So let's just first start off with what we've already been doing so far. So let's give this a try. So I'm just going to try thinking about it like a series of steps where each one is going to be a set of choices. So imagine I have it like this. I'm just going to assign the roles at each step. So first, imagine I'm going to assign the float worker first, and I'm going to assign the general cashier, and then I'm going to assign the cashier and cash office, so the cash office worker. So I'm going to splay them out just like I had before with all my possibilities. So now notice here that if I start off with the float worker, remember Bob cannot be a float worker. So I have 3 possibilities, either Alice, Charlie, or Drake. So you notice at the first step, I have 3 possibilities, right? Now, if I pick Alice, then notice that for the general cashier, I can pick one of the 3 remaining workers that I have. Bob is qualified to work as general cashier. So is Charlie. So is Drake. So if I pick Alice as the float worker, then the other 3 workers can work as general cashiers. Hence, I have 3 possibilities. And then, of course, if I were to, say, pick Bob as the general cashier, then I know, because of my constraints, either Charlie or Drake must be the cash office worker. So I've just traced out the first path along the top. If you follow along, you can even take your finger and just like draw like this with your line. And you'll notice that I either get those two possibilities at the end if I pick Alice, then Bob. However, I want you to notice something. If I pick Alice, then Charlie as the general cashier, then it must be that Drake is in cash office. Because I already picked Charlie to be a general cashier. Remember, our constraints are in play. Likewise, if I pick Drake, then I know Charlie has to be in cash office. So you'll notice that in this case, if I list out all the possibilities in this fashion, you can keep looking at my diagram here. Take your time. You'll notice that if I count up the number of possibilities, you'll notice that I have 8 possibilities. So if I splay them out like this, I can indeed enumerate all possibilities. So this is one way you could splay them out. However, you'll notice that there's something a little bit odd about this. I want you to observe is that the number of choices are not constant at either of these 2 steps that I've given you here, the ones I've indicated in red. So notice that when I select the general cashier from step 1 to step 2, you'll notice that because I sometimes select Alice, sometimes I pick Charlie, sometimes I pick Drake. Sometimes that actually changes how the constraints of how I assign the roles. It changes how I have to select the workers. So hence, they are not constant among the choices I make. Now remember, the objects themselves can be different, but the number of choices must be constant. So if you're looking at this picture, think about the number of branches. So you notice that with A, I have 3 branches going out. However, with C, I have 2 branches out. And D, I have 2 branches out. That's not constant, right? If it was constant, it would have to be that there's 2 leaving each one of those, or 3 leaving out each one of those, or maybe 1. I don't know. But the point is in that step, I have this issue. Likewise, in the next step, you'll notice that sometimes I pick Charlie, sometimes I pick Drake. And that ultimately forces me in the 3rd step to either pick Drake or Charlie. However, if I pick Bob, then that forces it to be either Charlie or Drake. But remember, I had to make that choice later on down the line. So notice that one of these actually mismatches. So hence, they're not a constant number of choices at that step either. So you might ask, okay, well, can I use the multiplication rule? Now, in this way I've organized it, the answer, of course, is no, because of the way I told you this. Because now the somethings now depend on the previous somethings. You got to think about these like steps for which each one doesn't necessarily depend on the previous one in terms of the number I count. The objects themselves can be different, but the number I actually count must be the same in terms of each one of these steps. Hopefully this is clear. What's the issue here? So I'm going to show you how I can actually fix this idea that I've been doing so I can use the multiplication rule. Now, I want to stress for you that in our constraints, it doesn't say that I have to pick them in a very specific order. I've decided that order myself. So what I'm going to do is instead, I'm going to pick the order I've assigned the roles a little differently. It shouldn't affect anything because ultimately I'm still assigning those roles. And none of my constraints require me to pick them in a specific order. So let's try reordering the steps. So what I'm going to do is instead, because I know cash office either involves Charlie or Drake, I'm going to immediately pick that first. And there's only 2 choices here, Charlie or Drake. So if I look at my possibility tree, I'll call it a possibility tree at this stage because it lists out all the possibilities, right? So you'll notice that I have C or D after step 1. So just follow with your finger if you need to follow with your finger. So right now I'm sitting on C after start. Notice that after this I have to assign the float worker. Now remember, Bob cannot be a float worker. So that means if I pick 1, Charlie or Drake, that means that it must be Alice and whichever worker was not picked out of Charlie or Drake to be a float worker. So there's two choices, right? Likewise, for the third possibility, for our third something, remember, I got to keep my terminology straight. I'm using somethings, right? So the third something is going to be me assigning the cashier. Now, whatever I have left, I want to assign the third role. And I only have 2 workers left after each one of these choices because I've so far selected 2 workers. And I have 4 workers in total. So I have 2 choices. Now I want you to observe something. Unlike our example before, notice each one of these now has a constant number of ways that you can select for that step. So each one of them has, now it does not require that every single one is 2. It's just that each branch from each choice at a given step must be constant. So meaning that if I look at after my first step, when I see C and I'm going to decide between A and D for step number 2, when I've selected Charlie, you'll notice that it has to be 2 there because I have 2 possibilities. However, that means that any other one that could be a possibility after step 1 must also take 2 choices. So just to draw it out for you, here you go. Look at that. So I have all my possibilities here. So notice that I have 2 possibilities in step 1. So I have 2 choices, right? Charlie or Drake. Step 2, I have another 2 choices to make. So it's either going to be Alice or Drake. Or, in the other world where I selected Drake, it's going to be Alice or Charlie. So I have 2 possibilities to pick from here. And step 3, I have another 2. So in total, if I use the multiplication rule, because now I can, it's 2 times 2 times 2, which is 2 cubed, which is just 8, right? And it matches up exactly with even the approach we had before. Just now I can use the multiplication rule. So just to reiterate, just to remind you, just to draw this again for you. So in our previous example, we could not use the multiplication rule because we could not assume that each possibility at a given step didn't have a constant number of choices. Because in this case, they changed depending on prior choices that I made. So that's something to keep in the back of your mind when you're talking about this. So that's ultimately how we can use the multiplication rule when it comes to counting in this way. So there's a lot of different ways you can use the multiplication rule like this. A common example would be like if you're looking at the number of possible ways you can arrange a sequence of, say, passwords, or the number of license plates you can print, and there's no constraints in place other than, hey, look, it's either going to have an A, B, C, D, or some alphanumerical character. You'll have some number of characters or numbers you can select from at each step. You'll notice that if you splayed out all these possibilities, you'll get a possibility tree. And as long as at each one of these decisions, the branches leaving out at every single one of those states at that point are constant, then you can use the multiplication rule. That's the main point I want to take from this. I'm going to show you another interesting example. So imagine I give you a set with elements 1, 2, and 3. Now, just as a reminder, the power set of A is going to consist of the empty set, 1, 2, 3. Then there's another set, 1, 2. Remember, all these are sets, by the way. Then I have another set, 1, 3. Another set, 2, 3. And then I have a last set, 1, 2, 3. So just the set itself. Remember, this power set is all possible subsets of A. So now I want you to consider the following process. And I want to show you how you can construct any subset of A. And I want to show you just using this decision process. So at the beginning, I'm just going to assume that the set is the empty set. So at my start, I'm just going to have the empty set. So step 1, I'm going to have the empty set. Step 2, I'm either going to put the element 1 into P, which is the set that when you start off is the empty set. I'm going to put 1 into P, or I'm not going to put it into P. So I have two possibilities, right? It's either going to go into P or it's not going to go into P. The third step, I'm going to put the element 2 into P, or I'm not going to put it into P. So two choices. Likewise, in our final one, I can either put 3 into P or not into P. Two choices. So naturally, you want to ask yourself the following. So how many possible subsets can be produced by this process? Well, notice that each one of these possibilities has two choices. This is regardless of which element I put in or not put in, because each one of these somethings doesn't depend on what happens before that, but that's okay if it did, but it's just that the number of choices I make doesn't depend on the previous actions. It's always constant, regardless of which state I decide to be in. So here's the point. Notice that every single time I make two choices. So I end up with 2 cubed. So 2 times 2 times 2 is what the multiplication rule will tell me. And I get 8. But wait, this should look very familiar to you. Well, if I'm counting up how many possible subsets there can be, notice that my process either puts the element in the set or does not. And it does it for each element in A. But if you think about this, what we're really doing is actually quite familiar to us. Because we know how many elements are in the power set, right? Remember, the power set is all possible subsets. And we know that if I give you that the cardinality of A is equal to n, then you know that the cardinality of the power set is 2 to the power of n. So that means that if you think about this very carefully, I want you to think back to the lecture where I gave you the induction proof for the cardinality of the power set. In that proof, I used a very important idea where I was matching up I took each subset and I showed you how you can create a corresponding subset that contained an element. So I was able to take each one of these elements and I was able to show you how you can get another subset by appending another element into it. So it's either there's ones without the element in it or those with it. This should look eerily similar to you, because every single time I do this, I construct all the subsets that have all of these in there. Then I have all the subsets with the new element appended into it. Well, notice that really what we're doing here is eerily similar to that induction proof. Just the difference is that one just assumes that I've given you all the possible subsets of a given number. So it would be n-1 or something like this in our formula over there. And I'm showing you how you can get those extra elements by either considering the ones without and the ones with. And each one of those had to have been two choices, right? But remember, I showed you how that actually, the relationship there is that it multiplies it by 2. Look at the construction I have here. You can almost look at it like it was another step in the process, and each one had two choices, right? So I'll let you think about that. That's interesting. So here's another example. Now, the multiplication rule can be casted in terms of sets when you talk about the number of elements as a result of the Cartesian product. Now, actually, we've seen this idea actually way back. I think this is very close to the beginning of the course. So imagine I give you k sets, a sub 1, a sub 2, a sub 3, all the way up to a sub k. Then, if I wanted to know the number of elements in the resulting Cartesian product, so that would be a sub 1 times a sub 2 times a sub 3. So remember, those x's are denoting the Cartesian product. So the result I'll get here is a k-tuple. So I'll end up with a k-tuple or k-tuple. And if I look at how many there can be, it's going to end up being the cardinality of a sub 1 times the cardinality of a sub 2 times the cardinality of a sub 3 all the way up to the cardinality of a sub k. Now, you might naturally ask, okay, well, why is that? Well, let's use the same rationale and reasoning we were using before. Well, look at it. Okay, the first choice is a sub 1. Now, this is lowercase a sub 1. This is just some element in a sub 1. So I get to pick one from a sub 1. And I have a sub 1 choices, so capital A sub 1 choices. Same thing with the second set. Same thing with the third set. And so on, including up to the kth step. So by the same reasoning, we're using the multiplication rule, and that's how we could find out the number of elements in the resulting Cartesian product. So this is actually where it comes from. You can actually prove this using induction. So if you're wondering how you can prove the multiplication rule, it's through induction, and you can probably do it through this means, trying to do it with the Cartesian product here. But there's a bunch of different ways you can go about it. One natural way is just consider the formulation I gave here at the beginning, and you can prove it via induction that way. I don't have time to talk about that specific proof. I'm going to switch gears. I'm going to talk about a different rule. So now we're going to shift gears to talk about counting elements in sets. So I just remind you, I've been using this phrase cardinality. Remember, if I give you a finite set A, it's just the number of elements of the set. So for example, if I give you these two sets here, you'll notice that the first one here on the left has 4 elements, and the one on the right, notice that's just the power set of the elements 1, 2, and 3 in one set. That is going to be 8. So I'm going to talk about the addition rule next. So if I give you any finite set that equals the union of k distinct pairwise disjoint subsets, a sub 1, a sub 2, all the way up to a sub k. So this definition should glare at you, but I'm going to say what this is first. So if I have these couple properties in play, then I know that the cardinality of A is going to be the sum of all the cardinalities of those pairwise disjoint subsets. Now, notice that this is just a sum rule rather than a multiplication rule. Now, the reason why I want to bring this up is that notice that really this is actually hiding the definition of a partition, because you'll notice that it's the union of the pairwise disjoint subsets. So if I take A1, A2, and all the way up to AK, these are actually all the subsets that are all disjoint. When I union them all together, I get A. And they're pairwise disjoint. So keep that in mind. So this is really just me saying, hey, look, A sub 1, A sub 2, A sub K, they partition A. That's the main thing you should notice about this. So if they partition A, then the addition rule applies. So if you want to count up the number of elements in A, you can use the addition rule here. So I want to prove the addition rule for you. So I'm going to do it using induction. So I'm going to use particularly weak induction. So for any k greater or equal to 1, I'm going to let S of k denote the following statement. If a finite set A equals the union of, and I have two ofs there, please ignore that, of k pairwise disjoint subsets, A sub 1, A sub 2, all the way up to A sub k, then the cardinality of A is just the sum of all the cardinalities of A sub 1, A sub 2, A sub 3, all the way up to A sub k. So that's the statement I want to ultimately prove for all k greater or equal to 1. So the base step, I'm just going to consider when it's 1, right? Remember, we got to think about the analogy where I'm trying to teach the cat how to climb the ladder. So I got to put the cat's paws on the first rung. And now I just got to say, hey, look, S of 1 really just says that A is the set that equals one subset, right? Because remember, these subsets partition A, right? And I only have one set, right? So it means A sub 1 it equals one subset. That's just A, right? So A is equal to A sub 1. So you know the cardinalities of those two things have to be equal, right? So that means that S of 1 has to hold, right? So let's talk about the inductive step. So this is where it gets interesting. So I'm going to fix some k greater or equal to 1. Actually, that should say r. My apologies. That should say fix some r greater or equal to 1. So when you're following in the notes, just keep that in mind. I'm just making a small change after this. So fix some r greater or equal to 1. So I'm going to just assume that S of r is true. So I'm going to say it holds. So that's our inductive hypothesis. Then we need to prove S of r plus 1. And I want to show if that follows. So, I want you to notice that by definition, A has to equal A sub 1 union A sub 2 union A sub 3 all the way up to unioning A sub R plus 1. And each one is pairwise disjoint, right? Now, I want you to let B be A sub 1 union A sub 2 union A sub 3 union A all the way up to union A sub R. Now, I want you to observe that, hey, look, A is just equal to B union A sub R plus 1, right? Because all I'm doing is I've just truncated all of those unions together into B. And now I just want to tack on A sub R plus 1. But I want you to notice that B intersection A sub R plus 1 has to be empty. Because, remember, they're pairwise disjoint, right? So if I take the union of all of those other ones, they have to also... none of them contain A sub R plus 1, right? No element from A sub R plus 1. So I'm going to start off on the left-hand side of S of R plus 1, which that one tells me that the cardinality of A is equal to the cardinality of B union A sub R plus 1. Because remember, they're pairwise disjoint, meaning I'm not going to count anything twice. They're sitting off in different sets. So, and since B and A sub R are pairwise disjoint, I can split apart that union by definition. So, that being said, now I end up with the cardinality of B plus the cardinality of A sub R plus 1. But look at this. Look at this. What's B? What's B? Now, I didn't note it here on the slides because I wanted you to come and listen to this video. Notice that the cardinality of B, that's just literally our inductive hypothesis, right? That's just the union of all of the previous ones. So I'm just going to apply the inductive hypothesis, which you should state if you're trying to use this. But I've, just for the sake of time, didn't include it here. So notice that if I have the cardinality of B, notice that it's just really just the sum of all the cardinalities of the previous sets. So I just plop that in, and then you'll notice, hey look, I have a summation on this side that goes up to R, and I have the next element sitting right beside it. So I'm just going to combine that into my summation, and I end up with the result I ultimately wanted, right? Which, of course, is the right-hand side of S of R plus 1. Therefore, S of R plus 1 follows, and therefore, by the principle of mathematical induction, S of K is true for all K greater or equal to 1. So, note that should say K there. My apologies. So I want to show you how you can use this rule. So I want to start off with something that looks a little bit strange at first, but I want to illustrate how you can use this. There's a lot of ways you could use this rule. It's very valuable. So I'm going to ask a very simple question. How many 3-digit integers, so these are numbers like 150 or 256, they have 3 digits in them. So I want to consider the numbers from 100 to 999 inclusively. I want to ask how many of these are divisible by 5. Now, I'm just going to throw a fact at you, just to make this a little easier. So every non-negative integer that's divisible by 5 in its decimal representation either has a 5 or a 0 in its unit place. So I'm just going to use this fact to help me. So I'm going to denote A to be the set of integers 100, 101, 102, up to 999, such that 5 divides n. So, from my fact, it's either that x, if I pick some element x in A, then it either has in its decimal representation a 0 in its units place, or that it has a 5 in its units place. So I'm going to let A sub 1 be the subset that contains all the ones with 0 in their units place, and A sub 2 be the ones with the 5 in the units place. Clearly, they cannot overlap because 0 is not equal to 5, right? I'm pretty sure everybody could accept that from me. So then you'll notice that obviously the two subsets I've selected, A sub 1 and A sub 2, they partition A, so we're okay. So now I'm going to consider each one of my subsets. And you're going to notice something that's kind of neat here. I'm going to use the multiplication rule. So if I consider A sub 1, for example, the first of the 3 digits, so I'm talking about the highest order digit. So this would be in your hundreds digit. So I can either have a 1 in it, a 2, 3, 4, 5, 6, 7, 8, or 9. 9 choices there, right? So I'm going to put my first choice in. So remember, I'm just thinking about this like a process. I'm trying to construct the number. So I'm going to pick 1 through 9, one of those. So I have 9 choices. Then now in the second digit, the tens digit, I have 0 through 9, so I have 10 choices. And then ultimately, if it's A sub 1, it's going to have a 0 in it. And if it's A sub 2, it's going to have a 5 in it. So that means that there's only going to be one choice in the third digit, the units digit. So that means that if I want to find out the number of possibilities that could be sitting in that set, then you know that the cardinality of A sub 1 has to be 9 times 10 times 1. Each case this applies. Because fortunately, the third choice is just 1 for each one of them, which is nice. That's just a coincidence, but if you wanted to tackle this where the numbers were a little different in either case, you could tackle each one case by case. So if A sub 1 was a little different than A sub 2, as long as they partition A, we're okay. So all I'm going to do is use the addition rule now. So I'm just going to add A sub 1 size to A sub 2 size, the cardinalities of these, and add 90 plus 90, which is just 180. It's pretty nice, eh? So here's another rule that is useful to have. This is something to just put in your hat. Just like, hey, look, I have it right here. So if I give you a finite set and any subset B of A, then if I ever wanted to look at the set difference of A and B, then I notice that if I want to look at the size, then I just take the cardinality of A, subtract the cardinality of B. Now, you might naturally ask, well, why is this true? I want to imagine the Venn diagram of A and B. So imagine I have A right here, and I have B right here. We're going to know that A minus B will get rid of all the elements in B. But I want you to realize that the visualization I just gave you is actually not quite correct. What actually is, remember, it's a subset of A. So it means that actually B is hiding inside of A. So it means that when I take the difference, I'm just pulling out elements from A. I'm not losing anything beyond just those elements that are in B. Think of it like almost like a round piece of cheese. I'm just going in and I'm chopping a pull out of the cheese. And now I have these cheese. This is B. So for example, if I have A, where I have the elements 1 through 5, and then I just have B that's 2 and 4, you'll notice that I get 3 elements because, hey, look, B is a subset of A, and I'm just removing my little piece of cheese from my wheel of cheese. So that's just the difference rule. It's pretty straightforward. Now, this one's a very handy thing to have, especially if you're interested in probabilities or statistics. But I'm just going to state it here, and I'm going to give you the idea for the first case. And the second case, I'll let you think about it. So this is what's often called the inclusion-exclusion rule, sometimes called the inclusion-exclusion principle. So if I give you A and B, and these are finite sets, so they can be any finite sets, then if I want to take the union of A and B, and I want to determine the number of elements that are in A union B, then it is the cardinality of A plus the cardinality of B minus the intersection of A and B. Now, I put a picture here to help you out, just to visualize this. So remember, A union B will be literally if I took both of those sets, A and B, and I combined the elements together into one set. So it means if I were shading this Venn diagram, I would shade it everywhere inside of A and everywhere inside of B, including where they intersect. So you might ask naturally, well, why do we need to get rid of things? Well, think about it. if I added A and B to get their elements together, remember that I need to keep this in mind. I have all the elements from A, all the elements in B. However, look at that middle region there. When I do this, you'll notice that I did something actually technically twice. I counted the intersection of A and B twice. You'll notice because if I add in A, that includes some elements that might be in B. Likewise, when I add B, I'm going to include possibly some elements that are from A. Those ones that are intersecting. So it means that I've double counted that region in the middle. So I need to remove one of my extra counts. So if you're not convinced by this, try to draw out a set yourself, or try to list out the set and try to use this formula without removing the intersection. You'll realize you're actually double counting elements. In particular, the ones that are intersecting. That's why we have to subtract the intersection of A intersection B. Sorry. So that's why the way it is. In fact, the same principle applies with when you have 3 finite sets. It's very much the same idea in play. Things are being double counted. So you just got to make sure you kind of record keep those elements so you don't either double count or lose elements. And naturally you might ask, okay, well, how can I use this if I want to deal with intersections? Now, just remember, I gave you the other lecture a property for how you can convert between union and intersection. So you can use De Morgan's law to go between union and intersection. So if you find yourself wanting to use this rule with the intersection, you might find this pretty handy. So that's basically it when it comes to sets. I'm going to be shifting gears now. I've talked about these very broad general counting rules. I'm going to now restrict myself to some very specific kinds. Now, these are still rather general, so keep that in mind. So I'm going to first consider the idea of a permutation. So here's the definition of a permutation. A permutation is of a set of objects or elements. It's just an ordering of the objects or elements. You can imagine them being like in a row from left to right. So some people would think about these as ordered tuples. So I imagine I give you the elements and I want to signify their order. So for example, if I give you a set A, B, and C, where A and B and C are the elements in the set, the following are all the permutations of this set. So you'll notice that I have six possible permutations here. So I just take each possible way I can arrange A, B, and C. So I obviously have A, B, and C itself. Now naturally, I'm going to try permuting A and B like this. And maybe I want to permute C and basically I'm going to try all the different combinations in the same way and end up with 6 possible ones. Now something I want to address from mostly a combinatoric standpoint, each one of these objects, when I define or describe the permutation to you, has a position or index. So for example, my listing there where I have A, B, and C, you can number these like 1, 2, and 3, where their positions are 1, 2, and 3. And so, for example, if I look at the second one right to its right, where I have BAC, that would be read as 2, 1, 3. That's just something to keep in the back of your mind. You can think about these as encoding the positions, if you don't want to actually think about them as tangible, like the whole descriptions of the objects. So you can imagine you have your object, all the elements here, and it's telling it what what position those objects should belong in. So that's really the information you need to encode a permutation. That's just more of a formal thing I just wanted to point out. So remember, it's just one permutation is just a set of objects or orderings of said elements. So each one of these 6 here is a permutation of the set I've provided. But all 6 of them is the set of all possible permutations. So there's 6 possible permutations of this set. So I want to ask, how many permutations are possible? Well, remember, I gave you the rules for this already. I can use the multiplication rule. You can prove this with induction, by the way, but the multiplication rule is naturally inductive. So think about this. The permutation if I give you a set with 3 elements, you'll notice that I have how many choices for the first position? I have 3 elements to pick from, right? And then you'll notice that it kind of goes down from there because I can't repeat the element, right? So I get 1 less element. So in that case, I had 2 elements to pick from. Then I had 1 element to pick from. This generalizes more formally as follows. So now I end up with a n-step process where first I select an element to write first for my permutation. So there's n possible elements that could go in that first spot. So here's my first spot. There's one of n possibilities can go here. Now I've used 1 element here. That means the second one only can have n minus 1 possible elements. Then the third one. Hey, look, I already picked an element over here. Okay, so now I have 2 elements I've picked so far. That means I have 2 less elements I can pick from for the third position. So it means I have n minus 2 possible elements I could pick from for the third choice. And so on, all the way down to the nth choice, which ultimately I'm going to end up with 1 possible element I could pick from. So it means by the multiplication rule, because I can use that, because regardless of which element I put into the spot, the number of ways I can arrange the objects does not change depending on which choices I make, right? It's regardless if I put, in my example here, if I pick A as my first element, it doesn't affect the number of choices that make in the future, except for the number of ways I count them, right? So in this case, I start off with n, then I have n minus 1, but remember, it doesn't matter if it's A, B, or C in that first spot, right? The only thing that's going to be consistent for me to use the multiplication rule is that the number of ways I can count them is constant, regardless of which one of the choices I made in the past. So let's get back to this. I keep having to say these things because counting, everybody thinks counting is a very easy thing to do. Counting can be very challenging, but you have to just be careful because every time somebody formulates a problem for you, sometimes some little wrinkle comes in and then the counting becomes much harder to do. So that being said, the number of permutations possible, if I look at my process and I use the multiplication rule, it's n times n minus 1 times n minus 2 times all and so on until I multiply 2 times 1. Well, you may know this is n factorial, which is denoted by n with an exclamation mark right after it. So for example, 4 factorial is 4 times 3 times 2 times 1, which is just 24. Now, it's worth noting that 0 factorial is defined to be 1. Now, you might naturally ask, okay, well, why is it 1? Now, it's going to become more apparent when we get to it later, but I'm just going to motivate why 0 factorial would be 1. Okay, imagine I give you a set that is just the empty set. Imagine it's just the empty set. Okay, so there are no elements for me to permute here, right? There's just the empty set. Well, how many ways can I really permute the empty set, right? Well, there's just the empty set, right? There's just one possible way the elements could possibly be arranged, because there's none, right? There's no elements. So that means that if I wanted to count up the number of ways I can arrange no objects, well, that's just 1, right? That's the number of ways I can do it. That's one of the main reasons why 0 factorial is defined to be 1. It's very convenient also for some of our formulations later on. So just keep in the back of your mind this interpretation of that we're trying to really count sets or orderings of sets. So just keep that in the back of your mind. A lot of these rules will not seem as arbitrary if you keep that in the back of your mind. So just, I must stress this. So I'm going to do an example. So imagine I give you the word computer. So how many ways can I arrange the word computer by its letters? So I want you to observe that computer, the word computer, has no repeated letters in it. All the letters are unique. So that means that if I want to consider the number of permutations, I really just have to consider the number of permutations of the set when I contain the elements where each element is just one of the letters in the word computer. Remember, I'm just not doing anything too crazy, right? I just have all my letters, and I want to know how I can arrange all these possible letters. And all of them are unique. So that means I could just imagine this like a set, where each letter is in the set. And now I want you to notice, remember, they're distinct. So we have no duplicates. But there's 8 letters here, right? So the total number of ways I can arrange here by our definition, what we came up with, it's 8 factorial, which if you calculate it out, it's 40,320. Keep in mind, I didn't do that with my head. I'd use the calculator for this. So that's one example. I'm going to tweak the example slightly. So imagine I give you the word computer. But I want it so that I want to know how the number of ways you can arrange the word computer, but I want the C and the O in computer to stay together. So as long as you permute the elements such that C and O stay together. So remember in our old example here, I had each one of the letters inside of my set as an element, right? Well, I'm going to use the same idea. I'm going to imagine each one of these letters like a letter group. And I want to group C and O together. So now really, if I think about this in the same way, remember, all the letters are distinct, and I've just paired C and O together, which is distinct as well. You'll notice that now I have 7 elements in my set, because I have 7 letter groupings. So the total number of ways I can arrange all of them is 7 factorial. Remember, I just lost one letter group by the same principle. So if you calculate this out, it's 5,040. So hopefully this is clear to you. I just want to give you the basic ideas here. So let's continue here. So I'm going to define something called an r-permutation. So an r-permutation of a set of n elements is an ordered listing of r elements from the set of n elements. So I'm going to denote this as P of n and r. So this is going to be the number of r-permutations of a set of n elements. Now, you might naturally ask, so let me first say what it is. So it's n factorial divided by n minus r together, factorial. Now, you might ask, okay, well, what does that mean? Okay, so remember, this definition is saying that if I give you n elements and I want to know, I give you a listing of the elements, but I'm going to pick r of them from n. And I want to know all of them. Then this will give me that value. That's basically what this is saying. So, I want to justify why exactly this formulation is true. Now, I'm just going to use a very similar idea that I just used before. And you're going to find that, hey, look, there's nothing magic going on here. It's just the same idea again. So I'm just going to use the multiplication rule. You can prove this with induction as well. So I'm going to select the first element. I have n choices to pick from. Remember, this is the same idea. Second element, I have one less choice because I've already picked one element. The third element, I've already picked 2 elements, so I have n minus 2 possible choices when I pick that third element. Now, I'm only allowed to pick up to r elements here. So that means that you'll notice in my counting here, when I consider the second one, I have n minus 1, right? So when I have the rth choice, my rth element, it should be n minus r minus 1 together. Because remember, it's always one less than the current choice I've made, right? So if it's r, it should be r minus 1, just like third is n minus 2. So when I simplify this, I get n minus r plus 1. And then I multiply these all together. And if you actually take a look at this, you'll notice that if you look at my formulation there with n factorial over n minus r factorial, if you take that product on the very top, if you divide off, you can actually take off the extra terms by using n minus r factorial. Because notice it's just n factorial, except it stops right after n minus r plus 1. So when you look at that division down at the bottom where it has n minus r factorial together, That's just eliminating all the extra terms. So if you don't want to use that formulation, there's always you could just use n times n minus 1 times n minus 2 times all the way up to timesing or multiplying, to be precise, n minus r plus 1. So this just falls out of the multiplication rule. It's very much the same reasoning we used in the past. So the one we used here to derive n factorial. It's the same idea. We're just stopping at some point. We're not picking all possible objects. We're just going up to r. So in fact, if you look at this and you said, hey, look, I want to have an n permutation, like where r is equal to n, you'll notice that this is literally just n factorial, right? Because if you look at our formula over here on the top right here, you'll see that it'll be n factorial over n minus n factorial, which would just be 0 factorial, which is just 1, right? So let's do an example of using this idea. So I'm going to ask you a very simple question. How many ways can 3 of the letters of the word bytes be selected and written in a row? So I give you a word bytes, and I want the 3 permutations. So remember, when I say 3 permutations, that means I'm going to select 3 of them from bytes, because bytes is going to be all my letters in the word. So you can think about this as a set of each one of the letters. And notice that it has 5 letters in this set, right? Well, look at it. I just want all the ways I can take 3 letters from the word bytes and put them together. Well, you'll notice that that's just p of 5 and 3, which if you calculate this out, you'll end up with 60. Now, I want to show you something a little bit clever. Okay, imagine you know that you need the last letter to always be a T in our 3 permutation. So our 3 permutation must always include T in it. And that has to be the 3rd position. So, if we think about it, we really can't use the 3rd position. So if I fix the 3rd position, we really only have 2 positions where we have to consider possibilities, right? So what does that mean? Well, the 3rd element is always T, and we only have 2 positions. Thus, the total number of ways I can select these is just going to be all the number of 2 permutations of the set where I remove T from here, right? Because remember, I already gave T a spot. T is always reserved in the 3rd position. So I only have 2 positions I can work with, but none of them can be T, right? So the number of choices I have goes down by 1, and the number of positions I can put those elements in is just 2, because I've lost it 1 to T, right? So now I'll have 4 elements to work with, and I want all the 2 permutations. So I could put them in, and then I could just tack on T on the end. Because remember, T is irrelevant here. Remember, it's like, imagine I'm just trying to count up all the possible pairs here. I could permute them. And I just want to kind of take sticky glue, like take a Post-it note, put T on it, and just stick it on there. That's basically what I'm doing here. So I have this formulation here. Notice I just go down by 1 element and 1 choice. My R goes down by 1. So now I have P of 4 and 2. And I calculate this out and I get 12. Now, I'm going to switch gears and talk about combinations. Now, combinations are quite related to permutations. I'm going to define an R combination as follows. So I'm going to assume that N and R are non-negative integers where R is less than or equal to N. So an R combination is a set of N elements, which is going to be a subset of R elements of these N elements. So just reiterating this, just because I feel like I need to say it again, I'll literally read the slide because I feel like I like the way I put it on the slide. An R combination of a set of N elements is a subset of R of the N elements. So I'm going to give you an example showing you all the possible R combinations given some R. So imagine I give you a set with A, B, C, and D in it as its N elements, so thus N is equal to 4. If I consider R is equal to 0, so this would be a 0 combination. So all possible 0 combinations, well, you'll notice it's just the empty set, right? I'm selecting a subset of 0 elements of the n. So just empty set. If r is 1, then I get to pick one element, and each one's going to be my possible subsets using only one element. So I have A, B, C, and D, each one in a set. So that case will be 4. When r is 2, you notice I'm going to have all possible pairings of 2 elements from A. But remember, these are subsets. They do not have an ordering attached to them. So that being said, you cannot have A, comma B, and then B, comma A in it. Those are just the same set, right? Remember, in a set, the order does not matter. So in R is 2, you'll notice I have 6 subsets, each one with 2 elements in it. So these are all 2 combinations. Each one is what we call a 2 combination of the set A. So R is 3. Then I have all the 3 combinations of set A listed out. There's 4 possibilities. So remember, each one of these is a set with 3 elements in it, and it's going to select from the n elements that I have in my set A. So each one of these sets here is a 3 combination of set A. Then finally, R is 4. Well, this is just the set itself, right? Because there's 4 elements. Now, I want you to observe something that's very neat, and we're going to talk more about this next time. Is notice that there's actually a symmetry going on here. Notice that R0 has 1 element. Sorry, it has one combination. Well, that was 0 combination. There's just one of them. Likewise, there's only one 4 combination of A. But you'll notice that the 4 and the 4 with R is 1 and R is 3, they both have the same number. Both 4 possible combinations. Then lastly, R is 2 and has 6. Notice that it's very symmetric the way it works. We'll talk more about that next class. But I want you to notice that if I take the union of all of these subsets, that I get the power set of A. Very interesting. That's interesting, isn't it? I'll let you keep that in the back of your head for next time, okay? So here's the thing I want you to keep in mind. Let me just make sure you had that. Okay, good. So I'm going to define what the number of possible R combinations is. So the number of R combinations of a set of n elements is what we would call n choose R, which is denoted as I have on the screen here, where n choose R is just simply going to be equal to n factorial over R factorial multiplied by all in the denominator, n minus R factorial together. So you might naturally ask, well, why is there that R permutation part in there before I get to that last step? Well, this is where the bridge between combinations and permutations occurs. So I want you to notice something. When we select R elements from a set of n elements, we get an R permutation, right? So remember, I told you that the number of possible ones of these is P of n and R, right? But I want you to notice something. When we consider R combinations, we don't care about the order that the elements appear, right? We just have subsets. And these subsets, the order doesn't matter. We just care about what's in the subset. So you'll notice that for each one of these subsets, in the R permutation, you're going to end up with all possible ways of permuting those elements. But I want you to notice that each one of these, say for example, in my example over here, if I have R as 2, you'll notice that I have always 2 elements in my subset of A, each case, right? Just 2 elements. But remember, if I consider an R permutation, there's only going to be 2, like if I have R as 2, then there's going to be 2 objects associated with each one of the R selections here. But I'm going to end up with all possible ways of arranging them. But how many ways can I arrange those objects? Well, that's R factorial, right? So each one of the objects I actually want is actually being magnified or overcounted by a multiplicative factor of r factorial. So we're going to divide by r factorial. So just to give you an example, so here are all the possible 3 permutations of the set A, B, and C. We've seen this one earlier. So notice I have 6 of these, right? But notice, I want you to notice that if you look at each one of these possible permutations of the set, they're really, if I ignore the order I've given them, they're all really just the same set, right? All of them. So if you actually were to plug this into my calculation for P3 and 3, you'll notice that I end up with 6 because that's the number of r permutations. In this case, it would be 3 permutations, which should match up perfectly with our definition of factorial, right? It should be 3 factorial. So now keep in mind that different examples will have a different number of these, what some combinatorists would call blocks of subsets, where we've ordered them, so they're permutations. So I have my permutations in blocks. In this case, I only have 1 block, and they're all going to collapse into a single element in the following way. So if I pick any one of those permutations, or 3 permutations of that set, notice that I can literally take any one of those and I can re-permute the elements so I can get another one there. So all of them are really just the same, but except for their ordering, right? Well, how many permutations are there of 3 elements? Well, it's 3 factorial, right? So that's just 6. So when I calculate this out, I end up with 3 choose 3, which ends up being 1. Note the red 3s there. That's the part that is removing that multiplicative factor of the r factorial. In this case, it was 3. So this is where the choose function, or what we call n choose r. So sometimes people will refer to what I've indicated here as n choose r as the choose function. So just keep that in mind. So I call it the choose function sometimes. But yeah, n choose r, this is how you can get it from permutations. And that's the bridge that keeps these two related. So I'm going to spend this last little bit of time introducing a couple more examples and introduce one more idea. So imagine you have 12 people. And I want them to join a team of 5 people. So how many ways can I arrange these 12 people so that I could pick? So I want to pick from these 12 people, and I want to make a team of 5. I know it's a little bit late here, so I apologize for me seeing a little stumbly here. So the point I'm getting at is that, so imagine you have 12 people that you want to join with a team of 5 people. How many ways can I give those 12 people an assignment to my team of 5? Well, notice that this is just really asking the question of the number of distinct teams. Well, that question is really just the number of subsets of 5 elements that come from the 12. Because remember, I have 12 people. I want to kind of take 5 of these people and put them into a team. I'm asking how many of these are possible. But really, that's just you using the choose function, or n choose r. But what's n? N is 12. R is 5. So if I calculate this out, unless I get 5,544. Now, I want to note this for you. Normally, you want to try to write out the factorial on the top so that you can try to cancel out obscene terms that get really large. So I'm just indicating that on the slide here. So I'll let you take a look at this for a moment. Even if you need to pause the video, pause the video. It makes things a little easier when you're calculating. So don't literally type in 12 factorial into your calculator unless you know it can handle those large numbers. I recommend massaging it a little bit. Just give it a little bit of a massage and simplify it a little bit by eliminating some of these extra terms. So combinations are pretty neat. But I want to, so that's normally where I don't allow repetitions, right? Because remember, they're subsets. These are subsets that I'm considering. What if I wanted to allow repetitions to occur? Remember I talked about the notion of a multi-set near the beginning of the course, where you allowed to have multiple elements in a given set? So that's a different conception of a set. Well, we're going to allow that to be the case here. So an R combination chosen from a set of n elements where repetitions of elements are allowed, that's what we're going to call an R combination with repetitions allowed. So I find this definition a little bit hard to follow at first, so I'm going to do an example. So keep in mind, I have a set A, and I'm going to select, I need to have R elements that are chosen from the set A, but it's worth noting that I'm allowed to repeat the elements from A. So I'm going to consider 3 combinations with repetitions allowed for the following set. So if I give you a set with 1, 2, and 3 in it, so a 3 combination should consist of 3 elements, and I'm allowing them to repeat. So I'm looking, so you gotta imagine this like I have 3 slots. 3 slots. I can pick in the first slot an element 1, 2, or 3. The second element, I'm allowed to technically pick 1 or 2 or 3. And the third element, I'm allowed to pick 1 or 2 or 3. So that's what I mean by repetition. So you're allowed to repeat elements in our, what we're calling, they're technically called multisets, but I'm going to use this vector-like notation or array notation just to indicate the difference between a set and this multiplicity being allowed in a set. So that's why I'm using square brackets here, by the way. So for example, one possible R combination of A where repetitions are allowed would be 1, 1, 1. Because, hey, look, I picked 1 from the set. I did it just 3 times, right? But I'm only allowed to pick 3 elements from the set A. That's the point. So I've listed here all the possible 3 combinations of repetitions allowed for 1, 2, and 3. You'll notice here that, remember, like I said, the order doesn't matter. Remember, we're considering elements by their like, we're not caring about the order they're in. That's what we care about when we talk about a permutation. In a combination, we care about what the elements are. The repeats matter, but the order does not. So, for example, 1, 1, 1 is different from 1, 1, 2, but if I give you 2, 1, 1, that's the same as 1, 1, 2. So, that being said, remember, the order doesn't matter, the multiplicities matter. So when I look at 1, 1, 1, that's not the same as literally writing 1 like I would with a set. When I say 1, I mean the curly braces. So just keep that in mind. So my example should hopefully hammer in this idea. So remember, we're considering R combinations with repetitions allowed. So this is like a generalization of this idea. But you'll notice that this is actually going to be by the same principle. It's going to be very similar. And I'm going to show you actually how this idea sounds really general, but actually it's really hiding underneath it the same idea of an R combination. And I'm going to show you how with this example. So suppose I gave you 15 cans of soda to select from. And there are 5 different kinds of sodas. So how many different ways can I select the 15 cans of sodas? Now remember, there's 5 different kinds of sodas. So for example, you could technically select 15 cans of soda, all of the same kind. Maybe half of them could be one kind, and maybe the other kind of slightly larger than a half, maybe is another kind. The point is that we need all the 15 combinations of the set 1, 2, 3, 4, 5, where each number represents a kind of soda, but we're allowing repeats. So it's worth noting that we're looking for when there's repeats allowed here. Because remember, I'm caring about how I'm selecting the 15 cans, and I have 5 different kinds of soda to pick from. So, for example, 1, 1, 1, 1. So I have 5 ones here. 1, 1, 1, 1, 1. That is one possible 15. That's one possible way of actually. Actually, there's a small typo here. That actually should technically be 15 ones in a row. Because remember the sorry, there's another typo here. I apologize. This should be 15 ones in a row. So I'll fix it in the slides when you see it. So there's 15 ones, and then there's 2, 3, 3, 5, 5, and then maybe imagine there's another 10 more 5s. So those would be 2 possible selections. And remember, I'm allowed to have repeats. Now, looking at it this way maybe isn't going to make things a lot more daunting. I'm going to show you a very simple way of transforming this problem so that it actually just looks like an R combination. Because it sounds a lot more daunting, right? Because there's a bunch of... I'm allowed to repeat the elements. It sounds way more general, but I'm actually going to show you a little cute little trick that you could use. So I'm going to look at this a little differently. So I'm going to give you 3 examples of possible selections. So imagine I have 5 soda cans of type soda 1. I have 3 soda cans of soda 2, 2 soda cans of soda 3, none of 0 of soda 4, and 5 of soda 5. You would agree with me that this technically can be used to create actually, I think I misspoke. My apologies. This actually should be valid. It should technically be a No, wait, never mind. My apologies. I apologize. I know this stuff in and out, but sometimes I question myself. Like I said, you always have to be careful when you're counting. So that's one example. You can take a look at these couple other examples as well. But the point I'm getting at is notice that I'm using symbols here to represent the number of sodas I've selected. So what I want to do is notice I have 5 categories. And I have X's to indicate how many sodas of a given category I'm using. So what I'm going to do is I'm going to use bars to represent each, to kind of separate each category from the number of sodas. And X's to represent each soda, like in my table here. So for example, I have 5 X's, then 3 X's, then 2 X's, then no X's, then 5 X's. So for example, I have 5 X's, then 3 X's, then 2 X's, then no X's, then 5 X's. So I'm going to use a bar to separate each category, like I have below, where I have 3 examples. They correspond to the ones in the table. So I'm going to have 4 bars because I have 5 categories, but I need 4 bars to separate the 5 categories. But I have 15 X's to work with, right? There's 15 cans of soda. So it means that there's really 19 symbols in my sequence here. So now you can look at this like a string with X's and bars. So now, instead of asking the really daunting question about these repetitions and whatnot, we're going to ask this other question that will ultimately answer our question. What is the number of distinct strings of 19 symbols that consist of 4 bars and 15 X's? So let's answer this using just R and choose R. So let's take a look. So if I have 19 symbols, so imagine I have 19 spots where I can put symbols down. Okay, there are 19 positions in the string. I'm going to number each position 1, 2, 3, 4, all the way up to 19. Now, it's true that 15 of these 19 positions are going to have an X in them. So position 1 might have an X in it, position 3 might have an X in it, position 4 might not have an X in it. The point is that the positions that I can use, I can represent as a set. This set has 19 elements in it, numbered 1 through 19. Now, if I'm able to select the 15 positions which are numbered in that set, so whichever 15 positions I select from there will give me some subset. So it gives me some subset of those. And then naturally, whichever ones I didn't pick out of my subset, those 4 are where the bars are going to go. And then I can construct the string in this fashion. But what is this? What is this? Okay, well, I just have to pick from my set here 15 positions, right? So I have 19 total positions. Choose 15 of the positions. Okay, well, when you calculate this out, you get 3,876. You notice how I simplified a little bit here. So, you'll notice here that I didn't actually ever need to use the information that they're about the repeats or anything like that. I was able to transform this problem by considering them as strings and counting the number of possible ways I could put those X's and bars in to deal with this much harder problem. Let me just check here. My apologies. Was I? Oh man, I apologize. I've been going ahead on this example and I didn't show you. I'm just going to reiterate it for you. Hopefully you've been following along with the slides here. I apologize. It's because when I'm recording this, I have to click my left mouse every single time to update the window here. So just, this is the table I'm referring to. So I'm just encoding the X's of each category. And each one of these, remember I have 19 symbols. I'll have 15 X's and 4 bars where the bars separate the X's, just like I have here. So I'm just asking if how to come up with the different ways you can assign the X's to those positions. And the key is just to encode the positions as elements in a set and realize that there's 19 elements and I have to pick 15 of those positions to put an X into it. And automatically when I know those ones, I know automatically, once I know those 15 positions, the other 4 just need to go slide right in. So that means that it's just 19 choose 15, and I end up with this number here. So that brings me more generally to talking about the following thing. So if I give you a number of R combinations with repetitions allowed from some set of n elements, you can also think about this in the way I was. The number of ways R objects can be selected from n categories of objects with repeats allowed. You end up with this formulation, R plus n minus 1, choose R. You might ask, okay, well, where the heck did that come from? Okay, well, look at this. Okay, how many categories did I have? I had 5. I had 5 kinds of soda. Sorry, yeah, I had 5 kinds of soda. But remember, that ultimately translated into 4 bars, 1 less than the category. And how many cans do I have? I have 15 cans, right? So if you look at this, you end up exactly getting what we had when you put in for R 15, and then you put in for the number of categories, which is just going to end up being 4, or the total number of kinds of cans is 5. So 5 is N, 15 is R. You end up with 15 plus 5 minus 1 is 19. Choose 15. And that's what we get here. So there it is right there. My apologies. So that being said, I just want to summarize this one thing with you. So choosing k elements from n. So just n elements. Here's the table I want you to remember. So if the order matters and repeats are allowed, you're going to ultimately use the multiplication rule. So if I have n elements and I get to choose from k, then I'm going to have n to the k. So just in our, so for example, if every single time I have the choice of either including, my apologies. Okay, let's go back to our, actually, never mind. Imagine I have a set with 1, 2, and 3 in it. Remember, I can either put 3 in, or 2, or 1. So there's n possibilities. Likewise, for the next one, I have 3, then 2, or 1. Another 3 possibilities. And for the final one, I have 1, or 2, or 3. And if I wanted to choose 3 elements from a set with 3 elements in it, then I'll get 3 to the 3 in that fashion. So really, this is just the multiplication rule. I've given it to you. So when the order does not matter when repeats are allowed, you get our formulation we had before. But when repetition is not allowed, when the order matters, it's just the number. It's the number of r permutations, or in our case, the number of k permutations. If I use k there, of a set with n elements. And when the order does not matter, remember, we're considering possible subsets, but repeats are not allowed, we just get n choose k. So anyways, with that being said, that's everything I have to say for now. So next time when we come back, we'll talk more about different counting principles. We're going to start talking about why exactly the choose function operates kind of like the way it does. I alluded to this example where we've seen some symmetry earlier. I'm going to talk more about that next day, along with a couple other neat things like the binomial theorem and possibly the pigeonhole principle. So that being said, thank you so much and have yourself a beautiful day.